It's Jianheng Wu on behalf of the Fields Institute and on behalf of Kuma, Dr. Moody. I am very pleased to have Dr. Izadi with us today to talk about the generalized additive models to capture the death rates in Canada due to COVID-19. So Dr. Izadi actually was here in Toronto with a postdoc of, under the academic supervision of Professor Moody, and he has been a faculty member at Urmia University for a number of years before, and he is he's settling down now in Toronto. And I just want to apologize on behalf of Kuma. He was called by the Ontario COVID-19 command table for a special meeting, and he wants to send his regrets. So with that, Farzali, so you can start.
Okay, thank you very much, Professor Wu. My talk, first of all, good morning to everyone, and also good afternoon to all the people on the other side of the group, if there is any. My talk is generalized additive models to capture the death rates in Canada COVID-19. The data actually I got from the government of Canada is from January 13, 2020 until June 15, just last week. I was updating every week so this is the first slide. The top panel is time series, the whole Canada death rates. The second one is the trend going down, up and a little bit going down. And the third one is seasonal or cyclic. And the other one, just a random or white noise. You can see this, so I separated because there's, after the whole Canada, there are maybe 3 provinces. The left panel is the deaths above the whole Canada, and the right panel, actually this is, I think I missed one. I don't know what's happening here. Yeah, this one is Ontario, this one is the Alberta, but I think it should be, I don't know, it should be something I missed yeah, okay. Canada, Ontario, and British Columbia. And this is the box plot to see if there is any outlier. For the Canada, the red one, there is no outlier. For Quebec, we just one outlier. For Ontario, the blue one, there is no outlier. For Alberta, we have maybe 4 outliers. If we go plot the histogram of this, as you see from the histogram, also the density plot, the histogram chart on the 0 are very high, almost in all cases, maybe possibly not in the Alberta. So the top left is the whole Canada, top right is the Quebec, and bottom left Ontario, and bottom right is Alberta. And also, if we calculate the ratio of variance to the mean, for Canada we have 50, is very large number. Also, this shows that substantial overdispersion in the data. For the Quebec, we have 39 or 40. For Ontario, we have 17, and for Alberta, actually, we have 2, is not a big number. This rate in Alberta, it seems it not so natural. So what is the generalized additive model or GAM model? In general, the GAM has a structure something like this. we have yi as the response variable, and xi's are independent variables. If we have, a g is the link, what is called this link function, can be identity, can be log, can be exponential, different functions. If we don't have, just make the long story short, if we make only G identity, here if we make G identity and remove all other function F1, F2, and so on and so forth, we have just a ordinary list, just a linear, what is called general model. And if we add link function, which is not identity, to the left-hand side, we got the generalized linear model. If we add also these functions, which are called the smoothers, we got general additive models. And as we see, the mu I is the expected value of yi, and yi can be any exponential or even non-exponential family distribution. If you take a look on the functions, there's a very famous theorem by Kolmogorov-Arnold, which is Kolmogorov-Arnold representation theorem, says that any multivariate function can be represented as sums and composition of univariate functions. So what we can get from this function, we don't need even to write two variable function. Just one variable is okay if we can precisely get the algorithm out of this representation theorem. The FG function are called smoothers, and then taking into account all things, the ordinary least square problem generalizes into L of alpha. Alpha actually was the parameter for the linear part, which is called this parameters. The other also, we will see there are parameters. Because of that, we call this sometimes semi-parameter models. And we can write the whole thing as generalized additive model is the norm of y minus x alpha squared plus sum of lambda j integral. Integral is second derivative to the squared. And by a theorem, we can write every function in terms of bij's, which are called basis function. And for each function, we already select how many numbers we can give to write this function. There is also one elegant theorem says that usually in the beginning, we should take bij's as any polynomial function, but the theory says that we don't need more than cubic polynomial. Actually, cubic polynomial is enough to write any function with any number of cases. After calculating the integral, which gives us the quadratic form, and plugging in the above equation, we got this L alpha beta norm squared plus 1/2, which coming from, just for simplicity, the quadratic form, sigma lambda j, the beta t, sc, and beta. And as many as if we have, so as many as s and lambda is called smoother parameter, controlling the extent of penalization, and establishes its trade-off between the goodness of fit and the smoothness of the model. If we write this all S lambda matrix in one term, then we have this short form of the above expression. Therefore, by writing beta as so we have this alpha for linear part. Also, there are other betas on the integral part. If we add them together, we got the beta, new beta as alpha and beta. We can write this function as estimating beta given lambda as beta hat is arg min of beta norm a y minus x beta squared plus lambda times beta t s beta. We need also to estimate lambda smoothing parameter by different approach. I wrote here by generalized cross-validation, AKIAC information criterion, and restricted maximum likelihood. And we use this to for inference, where we have beta hat is the matrix form x transpose x plus lambda s minus 1 x t y. As I said, in the histogram plot, due to overdispersion in the death rates, we use the negative binomial. Suppose if yk is a death on day k, and let y follows a negative binomial distribution with mean mu k and variance mu k plus mu k squared divided by r. And for the binomial distribution PMF, with this parameter p equal to mu k divided by mu k plus r, we can write it as you see the PMF in this form. And R is the number of failure until the experiment is stopped, which is a like counting number, but it can be also real. P between 0 and 1, success probability in experiment, which is real number. Let G, which is I called link function, is a function of mu and written as a four function. F day of week, bi-week, and F day of month. F is a smooth function of time tk measured in days, and the other function are a zero mean cyclic smooth of the day of week, day of the bi-week, and day of the month. And we have this relation fh, the function at 0 equal to function at t. T can be 1 week or 2 weeks and 1 month, and n is 0, 1, or 2. Means that the function itself, because of the cyclicality, is equal to f0 to f2, and also the first derivative and second derivative. We have this three-dimensional for the base data. The x-axis is day of the day, and y is day of the week, and z is days. We can see that this is for whole Canada, a little saddle point on the middle. And in the case of Quebec, the saddle point is very sharp. Also, we have a local minima. For the Ontario case, become smoother. And for Alberta case, the saddle is very deep. As I said, Alberta is not so normal. Based on very recent paper by Verity et al., the distribution of the time from onset of symptoms to death for fatal cases can be modeled by a gamma distribution with mean 17.8 and variance of, I think, 7, it should be mistake, 7.12, or the standard deviation of, no, but probably 71.2, the standard deviation of 8.44. We use this for actually get the median posterior median in our model. So I use this GAM model for the case of Canada for two variables, S of day and S of day of the week. As you see, we have lots of parameters here. The intercept you see is 3 star. 3 star means 100% or on the level of 0 significantly, statistically significant. And the S-day variable also on level of 0 significant, and S-day of week also significant, but on the level of 0.05. And the R squared is 85, which almost good, and deviance explained is 92. And this scale estimation is the smoothing parameter. We got this restricted maximum likelihood approach, which is 1. If you see here, we have this in the top part, S a day, we have 19. For S a day, we have 15. This actually 19 is the rank of basis function. Means that for S a day, we supply k equal 20 for the rank function for the basis set. For the S day of week, because the is cyclic of 7 days, we have to give this 7, but we got 5 variables. You see, for intercept, we have one number for S day 1 until S day 19. We have S day 19, so for the day we have 19 basis function, and for S day of week we have 5. If we get the model metrics, is model metrics 103 is the number of days we collected data, and 25 is the whole coefficient metrics we got. I just get this because of the space here. I got just 7 by 7 of this model metrics. Actually, when I was preparing this presentation and the paper, like about 1 month ago, the data was not enough to get the significant results. And then I tried, this is maybe unhuman philosophy that we have to wait for more days to get a good fit, to get a good model. But I tried, like in Canada cases, this is, right, sorry. So this is day and day of week. And also I tried day and day of by week. And in day of by week, we have 19 again for day. By week, we have 12 basis elements. And still we have 3 star significant level for the intercept. For the also S a day, 3 star, 100% significant. And by week, we have 0.05 significant level. And again, in this case, the R squared and adjusted R squared almost the same, and scale is the same, and deviance is 92%. Also, I try to do S a day, day of week, and day of months. And in the day of months also, we have 3 star significant for intercept, 3 star significant for day, 1 star, which is 0.05, and the dot, which is 0.1 statistically significant. And again, this 85% adjusted R squared. We have, actually, I don't know, you can see my screen, this function. So for the Canada data posterior modes, the function, this two function, f s of day and s day of the week with 95 confidence interval. And the autocorrelation function, if you look at carefully, there is no lag, significant lag, which shows that the model almost perfect. Also, this deviance residuals are symmetric around the x-axis. We have the same for, also this is the Canada, and then we have the same, yeah, also QQ plot for the Canada, QQ plot. The top plot on the left is a QQ plot. If we have the data on the like red line, which is very strict, and this is a good, and top left is the residual against predicted. They should be symmetric with respect to x-axis. The histogram should be symmetric with respect to x equal to 0, which almost is the case. And on the bottom right is the response fitted, and it is almost symmetric on the y equal to x-axis. From this point of view, we say that the model is fitted so well. Now, same we have for Quebec, but Quebec we have S day, S of the S day, day and day of week, and intercept highly significant. Also, day of week highly significant. Day of week significant on the level of 0.05, and but the R squared is a little bit, maybe 10% less than in the Canada case. And we have, yeah, for in this case, you see in this 6 is the number of basis function for day, and 1 the number of basis function for S of day. So this is for Quebec case, day by week, and again, statistically significant for intercept. For day, statistically significant, but for biweekly, we don't have significant. And again, this R squared is 71%, and again, scale estimate is 1. This is for, again, for Quebec, day of week, and day of months. And we see that intercept is highly significant. The day of day is highly significant. Day of week highly significant, but day of months is not significant. And adjusted R squared 73. And we have the smooth function with 95 confidence interval. The first F day of week, the second F, the first is top left is F day, and top right if they are weak. And autocorrelation, I don't know if we can see, Yeah, it is not, I can see, yeah, no. Autocorrelation function, there is no significant lag. This is perfect. And also the symmetric deviance residuals. This is for day of week, day of months for Quebec. We have one more day of week function on the bottom left, and just almost all lags are not significant, but the lag 2, 3, 4, 5, 6, 7, 8. 8 is little bit significant, which shows that the model a little bit not fitted well to the data. And this is also QQ plot, histogram. QQ plot is on the red line. Histogram is symmetric around x equal to 0. And the top right is symmetric with respect to y equal to 0. And the bottom left is should be symmetric around y equal to x, but is not comparing to the Canada case. Ontario day and day of the week, we have 3 star significant for intercept, 3 star for day significant, and 1 star which is 0.05 significant. And the R squared is 81%. Ontario with day and by week, here we have significant intercept, highly significant, day highly significant, but bi-weekly is not significant. Day of months and day of week and day of months for Ontario. 2 highly significant intercept, day and day of months, and day of week significant on the level of 0.05. And the adjusted R squared also 82%. We have the smoother function for the Ontario, F, top left, F day of week, top right, and the autocorrelation function, we have only 1 lag, maybe 8 or 9, significant, and this deviance residual is also symmetric around the x equal to 0. There is Ontario day and by week. So if you compare this, this is day of week on the top right, and this is by week on the top right, different. But for the F, almost the same. But in this case, we don't have any significant lag on the autocorrelation function. Ontario day of week, Ontario day of week, and day of monthly with 95 confidence interval, but we have 1 lag significant. The same, we have almost QQ plot is perfect. Histogram is also 90% good. The top right plot symmetric around x equal to y equal to 0, and the other one around y equal to x is almost symmetric. Alberta is like what we see here. Even as I said, the Alberta case is not so normal. For intercept, even we didn't have just 1 star significant. There is no significant for intercept, but for day and day of week, we have significant levels. and adjusted R squared is just 27%, is nothing. So this shows that really data for Alberta is not good, is not normal. Again, for day and by week we have, so we see that for day and day of week, the intercept is not significant, but the two other is significant, with the adjusted R squared very low. But when we take day by week, we have this 3 intercept day by week, all statistically significant, and R squared raised to 72%, which is very high comparing to 25 or something. We have here 27 is very high. So this shows that sometimes which model is good for which data. In the case of Alberta, we see that we take the by week and day is better than other models comparing to Alberta, comparing to Canada and Quebec and Ontario. This is for day of week and day of months. We have, again, for intercept, no significant. Day is significant, day of week significant, but day of months is not significant. Still, we have adjusted R squared is 27. And for the Alberta case, these are the smooth function with 95 confidence interval. We have one lag significant, 1, 2, 3, 4, 5, 6, 7, 8 in the lag 8. This is Alberta S-day by week. And for S-day of week, S-day of months. So this top left FF day, this one day of week, and the bottom left day of week, and this is the autocorrelation function, which I can see any significant lag. So this case is a little bit better. This is the Canada and Quebec. Canada is the left panel, the Quebec is right panel, which shows that underlying death rates with confidence intervals, 95 confidence intervals, when we exclude biweekly cycle with smooth function of S of day and S of by day, by week. The scaled red bar chart illustrates the distribution of the location of the peak of the death rate curve obtained by simulation from multivariate normal random deviates of posterior modes for each model. We take the 1000 replica for each case. Same is Ontario, Alberta. And we have this function infected, inferred Canada fatal infection profile over time, S-day of week. The red curve shows the posterior median. The dashed curves shows 80% and dotted curves 90% confidence interval for the posterior median. The scaled bar chart shows the posterior distribution of the day of the peak of fatal infection. The gray curve, which is on the bottom, is proportional to the squared second difference of the median infection profile on the log scale, which is proportional to the smoothing penalty. And the green curve is proportional to the absolute gradient of the infection profile. And this is also for day of week and Quebec case. We see that for Quebec case, a little bit very messy. And this is the best book for generalized additive model. The first and the last is, the second edition is 2017, which is very good for all of this stuff. And thank you very much.